Okay, we'll start. All right, so we'll continue talking about secure tunnels. Is there any questions, by the way, before we start?
Yeah, sir,
Yeah.
so we are still in HTTPS, right?
So sort of yes. Or yes, let's just say yes, yeah. Yeah. Is that the question?
Yeah.
Okay. I thought there would be a follow-up. Yeah. Yeah, so where we're going with this is towards a protocol called HTTPS. Okay. So we have a user, Alice. I'm going to try and write clearer. We have a web server, say Concordia. We have this analogy of a secure tunnel, digital tunnel. And packets can flow in either direction over the secure tunnel. Okay, so that's what we're trying to build. We can have an adversary. The adversary is in the middle. How does the adversary get in the middle? It could be BGP, hijacking, ARP spoofing, any of those types of things. But this secure tunnel should work even if there's an adversary in the middle. Okay, so it shouldn't matter that there's an adversary in the middle.
Is Wireshark considered something like this to the guy in the middle?
Wireshark is a packet sniffer.
Yeah.
You can run it. Normally, you would want to run it in the middle. Otherwise, you're not going to see anything interesting. It has techniques for trying to break secure tunnels in half. But usually it requires you on your computer, to grant it permission to break it in half. So it will, if you're running it close to your computer, you'll give it, basically what you'll do is you'll allow it to install a root certificate, and then it can break any of your HTTPS connections. But, yeah. Okay, what do we want from the secure tunnel in terms of security properties? So what do we expect the secure tunnel to do for us?
Transfer the data in like maintaining the confidentiality, integrity, and authentication.
Okay. So there's more than one property we want. There's three. So the first one is confidentiality. So we want any messages or data that's sent to say secret from the person in the middle. Okay, so Alice sees the data, Concordia sees the data, but anyone in the middle is not going to see it. The second one you don't always think of, but is very important, is message integrity. This means that the data that gets dropped into the tunnel comes out the other end exactly the same, and if it doesn't, you can detect it. Okay. Sometimes you actually care about integrity and you don't care about confidentiality. So if I'm downloading, say, a software, I don't want someone in the middle to throw malware into the software, okay? But I don't care if they see it or not. They can see it. I just care about integrity. And then the third thing is authentication, but I'm not quite sure what that means. So can someone explain it to me?
It means for the non-repudiation?
So that's different. So that would be, if I send a message, I can't deny having sent it.
Okay.
Generally, a secure tunnel doesn't give you non-repudiation.
Authentication is like only the authentic user that would be able to.
Okay, so it has something to do with the user's identity. Okay.
To be sure that it's the person that you think is you're talking to. So it's to be sure that you're talking to the right server, for example.
Mm-hmm. Okay. So what it's going to do is it's going to make sure that we know basically the endpoints of the tunnel. Okay, we know where the tunnel starts and where the tunnel ends. All right. Now, there's different kinds of secure tunnels. There are secure tunnels that authenticate both the user and the server, the sender and the recipient. And then there's tunnels that just do one. So usually the server is more important. So when your browser connects to concordia.ca, it's going to try and make sure it's connected to Concordia, the company, the university. But Concordia isn't going to know who you are. It's not going to authenticate who you are using the secure tunnel. Okay? Once you have the secure tunnel in place, you might do something like log in with a username password. That's how they're going to figure out who you are, okay? But that's a different step. That's something that's happening inside the tunnel itself. There are protocols that do what's called client-side authentication. The main protocol that we're talking about, the question earlier, was eventually we're going to talk about something called HTTPS more specifically. It does have support for client-side authentication, but no one uses it almost. Okay, so it's unused. Most people just do one-way authentication, which is server authentication. So I'm going to write server authentication. And then I'll note as a kind of optional property, you might have client authentication.
So, sir, what's the difference?
Okay, so server is, I know where the tunnel ends.
Okay.
So I know it ends at Concordia. This is really important because what if the tunnel ends at the man in the middle? Or what if the tunnel ends somewhere else? Then the tunnel itself can be bulletproof. It has perfect confidentiality, perfect integrity, but all it is securely dropping the data into the adversary's lap. Okay, so that's not something that we want. All right. So server authentication is sort of like where the tunnel ends. And the person who cares about where the tunnel ends is Alice, because she sees where it starts. She knows where it starts. She's putting the data in the start. She just doesn't know where it ends. It ends out on the network somewhere. Okay. Client authentication would be the opposite. It's like where the tunnel starts. And the person that cares about it is Concordia. So Concordia, again, they know where the data is coming from. They know this end of the tunnel. They can't see this end of the tunnel because it's out on the network somewhere. Okay, so if both endpoints of the tunnel are authenticated to each other, then that's mutual authentication or server-client authentication. So sometimes we say mutual authentication. But generally, for a lot of protocols like the web, what we do is we authenticate the server, and we don't authenticate ourselves. Okay, why is that? Why, if you had to guess?
Because it's not important for the server to know who I am.
Okay, so in a lot of cases, it's not important. But let's say it becomes important, like you're trying to log into Google. And so now Google's like, okay, why don't they just do client authentication at that point?
Because there's too many users, right? To keep track of all the...
It's fine. I mean, keeping track of passwords for every user is also complicated. So it's a good guess, but it's the same complexity. Yeah, so let's say that it's about the same. So you're going to do some cryptography in either case. You're either going to take a password off the user, you're going to do some hashing of it. In this case, you're going to, like the way that you do this is just with Diffie-Hellman. So the client signs their Diffie-Hellman parameters, now you know who they are. They have a certificate that says who they are. Yeah.
Because on the client side, you have so much variables to account for, unlike on the server side. For example, you can't really dictate who is in front of the laptop trying to use the system to access it.
So it's a good guess, but laptops can do this, your phone can do it, the support is there in the library. It's instant, like you don't even feel it. It is a little more complex than typing a password in, but at the same time, like you won't feel the difference. You're already doing, like you're doing some cryptography to set up the secure tunnel anyways. It's not that much more over and beyond what you're doing, yeah.
Does it have anything to do with proof of work?
No, good guess, but no, yeah.
Is it sync acknowledge?
Nope. Yeah.
Does that have some certificates?
Sure. So it does, yeah. So who needs a certificate if we have mutual authentication?
The server needs to know that each client will have a certificate.
Okay, so servers need certificates. We already live in that world. Now clients also need certificates. So if we lived in mutual authentication, you would have to go and get a certificate for yourself. And the other thing that goes along with that is certificates have a key, and you have to store that key. Okay? So it's a little different than remembering a password. Remembering a password is easier. Now, we are moving to a world like with secure keys and things like that, where maybe you are going to be storing keys anyways. Maybe eventually we will just switch on client authentication. If you have a key that's stored anyways on your computer, it could do it. The experience is great. You go to a website and you don't do anything. You're just logged in automatically because your browser goes and fetches the key from memory. It does it. The server knows who you are. Okay? But we would all have to get certificates, and we would have to store the key that goes along with the certificate. Okay? So it's more of a usability thing for why we don't tend to do this way, or at least the web evolved in such a way that we don't do it. Okay. Now, we saw a bunch of crypto. Okay, we saw encryption, MACs, signatures, all of that stuff, certificates, Diffie-Hellman. Okay. Which of all the crypto primitives, which have to do with message confidentiality? Do signatures
No.
give you message? No.
Encryption?
Okay, so encryption's the main primitive here. Okay, so confidentiality is going to be taken care of by encryption. And it's going to be symmetric key. What about message integrity?
Match?
Okay, so MAC and signatures are the two things that we have. For this secure channel, it's mainly going to be MACs. Okay, so that's the symmetric key. What about where the tunnel ends?
Diffie-Hellman?
Okay, so this will be everything that's involved in setting the keys up. Okay, so it could be Diffie-Hellman, so key exchange,
Or RSA?
or key transport. Yeah, I think we're using KE and KT. KT involves public key encryption. And key exchange involves a signature. And in this case, it's going to be the server's signature. So you just do Diffie-Hellman, but the server signs what they're sending you. If we do mutual authentication, the client also signs. Okay, so both of them give each other certificates, so they know each other's keys. And then when you do Diffie-Hellman, both of them sign. Now it's mutual authentication. In server authentication, just the server signs and the client doesn't sign. I'll draw that out. I'll draw out the case of server authentication. Okay, so in summary, the way you set up a secure tunnel is basically you start with the public key of the server. If it's a signature key, you can do key exchange. If it's an encryption key, you can do key transport. In both of these cases, at the end of doing this whole protocol, you're going to end up with a shared secret. Okay, we call it the master secret. There's a small technicality with the key exchange. The master secret isn't quite in the right format, so we run it through an extractor just to compress it. With key transport, you can pick one that's from the right distribution. Okay, so now we have a master secret. All right, and this is shared. So this is the server knows it, the client knows it. And the adversary, even if they're in the middle and they watch this whole key exchange happen, all the messages back and forth, or they watch the key transport happen, which would just be one message in one direction, they're not going to know what the master secret is. Okay, that's what these protocols guarantee. Let's go buy some space. All right, once we have the master secret, then what we're going to do is we're going to turn it into a set of keys. Okay, so we'll run it through what's called a PRG, pseudo-random generator. And what that gives us is unlimited randomness. And then we're usually going to create 2 or 4 keys. It depends on exactly how we want to do the encryption stage. We'll have a encryption key for the client. So everything that goes from client to server, I'll write it as, I'll just write C to S. And then when the server sends you stuff back, it will use a different key. And then if you are using Macs, you'll have the same thing. So you have a key for the Mac. You'll have one for the client will use to Mac things to the server, and another one that the server will use to Mac things back. Why you split keys isn't that important. It doesn't really solve any like high security. There's not like a big vulnerability if you just use the same key. It's sort of convention, and there might be some like corner cases where it helps to split the keys out. But anyways. Okay, so now we have a bunch of keys for encryption in Mac. Then what we're going to do is we're going to encrypt. I'll write it slightly different. I'll say we're going to do authenticated encryption on the data. Okay, and now our data, we have secure data.
So this is done every time you go, like, let's say you go to the Concordia website, right?
Yeah, it's
all these steps are always done.
correct.
Well, one or the other. Right?
Yep. Yes. Yeah. Exactly. So every time you go to Concordia, this will be done, and it's a little bit worse. It's not just when you go to Concordia. I'll just show you. So I go to Concordia. What's sort of happening behind the scenes? So something that we'll use a bit. It's a good thing to enable. You might have to turn on developer mode, but most browsers have something very similar, which is called Web Inspector. It lets you see things. And so when I go to Concordia, I'm actually opening a bunch of connections to other websites besides Concordia. So I download the main page from Concordia, but then I'm going to this Cassie Cloud. I'm going to Google Manager. I'm going to Typekit and TikTok, whatever. So there's a bunch of different servers. So I'm actually doing I'm opening an HTTPS connection to all of them. If you see a little lock beside it, that means it was an HTTPS. So even though I just downloaded one website from Concordia, it made me go and grab a bunch of stuff from elsewhere. And so I end up doing 10, 20 connections to 20 different websites, and all of them will follow the same thing. Yeah.
Why?
Why do I load them from different websites? It's just that Concordia doesn't want to necessarily store these things, or someone else is giving it to them. So let's say they have a TikTok video. That video is hosted by TikTok already. So instead of making a copy and putting it on their own servers, they'll just have people grab it from TikTok and they'll embed it in the website. Yeah. So these are all resources that are embedded into the website that just come from other places.
So is this API fetching?
Is it API fetching?
Yes.
So that's a term that describes how you would get the data itself. Generally not. So APIs usually, it depends how you define APIs. Here, what's happening is this is just hard-coded. So the path to that file is hard-coded into this HTTPS website. Yeah, there might be parameters that would turn it into an API. That just means that the way I have a resource, the way I want to serve it to you is instead of giving unique names to everything, I have like a pattern that I use to access it. Yeah. And then APIs are usually associated with things that aren't free. in which case there would have to be a token. But in order for me to fetch that, the token would have to be in my copy of the website. I could go in and dig that token out. So generally, APIs are usually thought more of as a client going directly to a data source, in particularly a paid data source, and getting information. Or Concordia is doing that behind the scenes. So instead of making the user do it, they fetch all the information. Now it belongs to them. So instead of making you go to TikTok, they grab it from TikTok over an API, and then they send it down to the client itself.
It's kind of deep links.
Sorry?
It's a deep links.
Perhaps, yeah.
Could Cassie Cloud be their database service?
Yeah, it could. It's something. Yeah. So it says CDN. That means Content Distribution Network, which is usually done for. It's usually done to manage things that get a lot of hits. But if you look at what they're downloading, it's called template.min. I think so. This CSS is a file for like the fonts and the layouts of websites. It's probably just a super common CSS file that lots and lots of people download. Like so many websites use it that whoever hosts it put it on a CDN in order to manage it. Yeah.
When you were typing the Concordia.ca,
Yeah.
when you were loading those pages, like downloading those pages,
Mhm.
how is decided that this kind of pages should be loaded as well, like simultaneously?
Yeah. So what happens is, okay. So first, they're not simultaneous. So that's the first thing. So if you look here, it all happens so fast that it looks almost simultaneous. But if you see this sort of graphic here, this is showing the time when I started and stopped downloading each resource. So they do come down kind of in a ripple. Why do I download them? It's because this is the very first file I download, which is the HTML. You can see it has a bunch of links, right? So it links to this image. So my computer first gets this HTML file. The HTML file says, fill in this box with this picture. Here's the URL for it. Now I have to go and visit that URL. Yeah?
So is rerouting those pages by the server side, like the Concordia side?
No, so this is all, I download, the first thing I download is this HTML document. Everything I download after is because this HTML document, which is running in my browser now. So I have a copy of my browser. That document is telling my browser to get it. So servers can't push stuff to you.
You can sort of see it if you look at the source, right? Maybe a bit.
Yeah. So you can see, if you go through the source, you'll see that everything here is something that shows up here. But then some of these things, like you might load some JavaScript. Then the JavaScript itself might go and start loading other stuff too. So you might not see an explicit link in the HTML document. Once you have JavaScript running, it can go to a server and get a list from the server of things it should download, like say an ad library, and then the server is telling it, and so you won't see it in the HTML document necessarily. But yeah.
Which browser you are using?
This is Safari.
So for Microsoft or Google, it would be the same thing or it would be different?
So so there's two questions. You mean this tool or the what you see?
Yeah.
Okay, what you see will probably be exactly the same, but you do have the power through JavaScript to send a website to some. First off, when Safari asks for it, it often advertises what it is. So it'll say, "Hi, I'm Safari version blah 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 blah." If Concordia wants, this is like why on your phone it's going to look different. Right, it's going to see the phone version of it, then yeah, it can choose to send you a different version. So that decision would be made by the server. If the server had something that was optimized for Chrome or for Edge, it could be different than the Safari. Generally though, the only time it does that is just between mobile devices and desktop web pages. And then otherwise, everything should come down the same. Like if you're on desktop in Chrome and desktop in Safari, it shouldn't make a difference. Yeah. And then in terms of this toolkit, I know it wasn't your question, but this tool interface is in all major browsers. So Edge has it, Chrome has it, Firefox has it. So if you want to play around with websites and see what's going on, you'll find this. Yeah.
For every request that it makes, it creates a secure tunnel.
So not necessarily. So it's up to the website itself. So I'll just, I know it's really small, you can't really see it, but let me see if I can find a hot link.
One thing you can do, you can copy it and paste it to the notepad, and you can reset the form.
Yeah, true. I was just looking to see if there's a quick example, but I'll just explain it in words. It's up to this itself. So the HTML website will say, go load this image. And when they give the source of where you should load the image from, they might say HTTPS or they might say HTTP. If they say HTTPS, it will be over a secure tunnel. If they say HTTP, it won't be over a secure tunnel.
It will be between the server and wherever the location is, the tunnel, right? It will be like between the client.
Sorry, I sort of lost the question.
So when you like, it will be up to HTTP, sorry, it will be up to the HTML. Because HTTPS will create a new tunnel, or will be like the same tunnel?
Okay, so it will, okay, so there's two questions here. One is, let's say you're going back to the same host. So you see, like, I'm on concordia.ca, I get the HTML, and then I start loading images also from concordia.ca. That will go over the same tunnel. So the tunnel is a session between me and Concordia, and as long as we're both sending stuff back and forth, we're not going to do a new tunnel for every resource. Yeah. So think of a tunnel as a session, and so it's between you and a website. But if they send me somewhere completely different, like say they send me to Google to download something, now I need a new tunnel between me and Google. Yeah. And whether that goes over HTTPS, the HTML will tell me, right? So generally speaking, if the base website is going over HTTPS, all the resources will have to be as well. If they are not, you get into this situation called mixed content, where some of the stuff on the website was secure and some of it wasn't. Browsers don't like mixed content. And now what they'll do is they'll start blocking things that weren't downloaded over HTTPS. And so, yeah, that's...
But why does it lock on all of those elements? Is it because that one, like, certificate in TLS, like, it represents all of the...
Sure.
Oh, yeah.
So when I went to Concordia in the first place, notice it's going to HTTPS, yeah? Okay, so because of that, that's the reason why that first file was downloaded over HTTPS.
Yeah.
Then if Concordia supports HTTPS, they're probably not going to weave in content that doesn't come over HTTPS. If they do, they're in danger of making the browser mad. And so the browser might do, it's sort of evolved over time. Now it's likely to just block content that wasn't downloaded over HTTPS. In past years, it might show you like a lock with a warning sign and say mixed content, and there's different things like that. Yeah. So anyone who's either in or has taken 6150 with me, I'll go through all of that sort of details. So like, yeah.
Yeah, I see.
So there'll be a whole bunch of content about that itself. But here I'm just sort of focused on the crypto side itself. Okay. All right. Okay. Now the authenticated encryption here could look different ways. Okay. So we could use what are called block ciphers. Or we could use stream ciphers. I don't care about the difference between them for this course. You'll care about them in 6110. But examples of a block cipher would be AES. And then there's older ones like triple DES. And then there's some other weird ones too. Stream cipher. Yeah, so an older one, legacy one, would be RC4. And then the newer ones is called Cha-Cha 20s. I think the only one that you'll see. Okay, for a stream cipher, you also need to add a MAC. And so normally with RC4, you would use what's called an HMAC, hash MAC. And for Cha-Cha 20, you tend to use one called Poly 1305. This is like a cipher suite. So we call these cipher suites. It's like a combination of crypto algorithms, and this one is sort of a lot of these are standardized by the U.S. government, so they're NIST certified, and then this one is not has nothing to do with NIST. It's from a crypto researcher, and it's like highly optimized and things like that. But generally, people like it just because they don't want to rely on U.S. stuff.
So currently, that one is used, right? Instead of RC4?
Yeah, exactly. Yeah. So RC4 actually has some problems with it, and now it's considered insecure. And so websites that still support RC4 are not considered secure. Yeah. So I'll try and show you some examples of that in a second. Okay. Now with these block ciphers, you also need a mode of operation. Okay. So we talked about this before. So you need a mode of operation. And you may also need a MAC as well. It depends. Some mode of operations have MACs built into them. So GCM is an example that has one built in. And then CBC would be a good example of one that does not have it in, and then you're going to have to put an HMAC with it as well. Okay, so if you go from start to finish, you'll see that you involve a lot of crypto. So if I want to set up a secure tunnel, let's say I am going to do Diffie-Hellman key exchange, so that's one protocol. It's going to be signed, okay? The signature here will be something like DSA or the elliptic curve version of it, which is called ECDSA. Here I'm going to do encryption. It's also confusingly going to be called RSA, although whether it's a signature or encryption differs. RSA is the other signature here. Okay, so I might say I'm going to do Diffie-Hellman. I'm going to use ECDSA as my signature with Diffie-Hellman. Then I'm going to switch over to symmetric key, and I'm going to use AES, and I'm going to use it in CBC mode, and I'm going to use an HMAC as my MAC. Okay, so the full thing that I'm using is DHE, Diffie-Hellman exchange, plus ECS DSA, plus AES, plus CBC, plus HMAC. Okay, so you'll see like this big string of like the 6 different crypto primitives that you use. All right, so I'll show you what that looks like.
So TLS is
Okay, so this is TLS. So TLS is the crypto basically that does the handshake and does the switch over to symmetric key and all of that type of stuff. Yeah, and then where TLS becomes HTTPS is more in terms of like how you split packets up, how much of the packet are you encrypting? Are you encrypting it kind of record by record? What's on the outside of the envelope? So like, are there packet numbers and things like that? What are you doing for control? And that type of stuff happens later. Yeah. So we'll walk through that as well in a bit.
Is the encryption in HTTPS.
Yeah. So you can think of HTTPS as HTTP, which is websites downloading, fetching, and like websites, and then HTTP without the S is the protocol for fetching website resources. So you go to a server, say, give me the index.html, that type of thing. Yeah. If you want to make it secure, you pump it into TLS.
So it becomes HTTPS.
And then it becomes HTTPS. Yeah. So it's a secure version with TLS. Yeah. I'll draw it out in a second, like the relationship between these things. And then all of that goes over what's called TCP, which is a network protocol. Or now there's a new version called HTTPS/3, version 3, and it goes over UDP. And so there's a protocol called QUIC, and so we'll talk about that as well. Okay, so how do you do, we sort of know at the crypto level all the primitives that we're going through. Now let's walk through step by step, like Alice says this to the server says this back. What's the sort of order and everything that's being said back and forth? So we call this the handshake.
And you mentioned that the newest version only uses the key exchange, right?
Yes, exactly. Yeah, so I could mention that as well somewhere. I'll get to that in a sec. Yeah, I know a good place to put that in. Okay, so I'm going to do it more like a ladder diagram where we're just going to send stuff back and forth. All right, so this is, say, Concordia. And this is our user, Alice. Okay, so www.concordia.ca, HTTPS, I'll write it fully. This is what guarantees that I go to the secure version. So I type in https.concordia.ca or / concordia.ca, and or I click on a link or something that's taking me there. Okay, what's the first thing that my computer is going to do? Okay, so first thing I need to do is I need to get an IP address because I don't know how to get to Concordia itself. Okay, so I'll actually go over to DNS and I'll say, hey, do you know the IP address for Concordia? And it will say, I know it. It's 132.205.244.70. Okay, and that is the actual IP address as of this morning. And by the way, if you type it into a browser, like you can always do that. So I can do 123. I actually have it there, 205.244.70, and then it takes me to Concordia as well. Okay, so so this is my IP address. All right, now I'm going to go talk to Concordia. And before we start doing TLS and HTTPS and all that stuff, I'm going to do a simple check, like a simple back and forth with Concordia, just to say, hey, I'm a computer, I'm here, I want to talk to you. And we're going to use a network protocol called TCP. And so TCP mandates that we do what's called a handshake. So what I do is I just send it a message called a SYN, synchronize. It acknowledges it. And then I send back an acknowledgement. So this is just TCP. It's something that you always do when you're using something called TCP. Okay. What is TCP? TCP is just a way of moving packets around on the internet. There's an alternative to it called UDP. In UDP, you do not do this back and forth. What does this back and forth establish? It establishes that you're able to receive packets as well as send them. This becomes important because you can lie about the IP address that's sending a packet, and so the response can go somewhere completely different. We'll talk about that. It's going to become a big problem when we switch we want to switch HTTPS from TCP to UDP, but we're going to have this problem, and so I'll introduce that problem a little later. Okay, so this is just a quick back and forth. We call it a three-way handshake. And even though it's a handshake, it has nothing to do with TLS. It's like just a network protocol handshake. Okay, and then before we were sort of hinting at the stack. So basically I have IP addresses. So I'm sending stuff with IP addresses. TCP is sort of like I'm sending 5 packets and the server receives 4 of them. Does it know which one's missing? Does it have a way of coming back and saying I'm missing packet 3 of 5? So that's the kind of stuff that TCP handles. Then the stuff we're sending back and forth is a conversation about the website itself. So that's HTTP. And then because we're encrypting it, it's TLS. Okay. So your sort of data, the browser sits up here. It kind of puts stuff into the top, and then the stuff that goes out on the network comes out the bottom. Okay, so we go through the stack this way. All right, and then there's different layers to the names for the layers of the stack and stuff that we don't really care about.
I know the OSI's layer for IP is network, TCP is transport, HTTP is what session?
So HTTP is application, and I actually drew this wrong. Thank you.
Application is at the top.
Yeah, so I should put HTTP at the top in TLS.
And TLS is session?
And TLS is controversial. It sometimes is presented as what's called session. but normally people don't like the OSI model. They think it doesn't really capture things. And so TLS is usually, it's like a wrapper for the transport, which is TCP. So it's a TCP wrapper. It sits between the application and transport. Some people call it session. It used to be called SSL before it was called TLS, which stands for Secure Session Layer. But now it's called TLS for Transport Layer Security. It's security for the transport layer. But it's sort of part of the transport layer, but it's something you do before the transport layer. So most people just think of it as sitting between the two. Yeah. Okay. All right. So now we've done our three-way handshake for TCP. So now we're ready to send packets back and forth. Okay. So the other thing I didn't mention is that there's usually a port. And so the port number will correspond to like you'll send it to an IP and you'll also send it to a port, okay? And so Concordia will be set up so that it expects HTTP traffic over one port and it expects HTTPS over a different, and then it can tell them apart, okay? And so your browser will fill it in as the default, which is 443 for HTTPS, okay? So HTTPS. And if it were just normal HTTP, it would be port 80. Okay, so these are just standards. You could, if the server was set up and the client were both set up to talk over another port, that's fine. You can talk over another port. Alice's ISP may filter it, or your router might filter it. But otherwise, if it can go through and both of them can talk over that port, it's fine. But everyone keeps 443 open because everyone knows it's for HTTPS traffic. And yeah, it will be the default. Okay. All right, so now what we're going to do is we'll get into the actual TLS handshake. So everything above this line is kind of like TCP stuff, and then everything below it is TLS. So the initiation always starts with the client. So client goes to a website. Websites don't just push. You're like on your browser and it's blank, and then all of a sudden you go to a website because that website pushed it to you. That doesn't happen, okay? It always starts with the client. The client fetches it from a website. And so what the client will do is they'll first say hi, essentially. So we call it a client hello. And I'm going to send some stuff with it. So because it's going over 443 and it's in the format of TLS, the server thinks it's TLS. There's a case that I try to go to a server that doesn't support TLS or doesn't support HTTPS. In that case, it's probably going to drop it just because it's coming over the wrong port, or it will just get a bunch of data and be like, I don't know how to parse it, okay? And then it just won't respond, and then my browser will show me a message that says server not responding, okay? So that's what happens if it's not expecting it, but we'll assume that the server's set up to expect it. So it's going to be client hello. What I'm going to do is I'm going to say what TLS versions I support. Okay, TLS comes in different versions. So
And that's from the browser or the operating system?
So the browser will, it could be either. And so let's call it the browser itself. So
It's always good to update the browser, right?
yeah, it's more complicated because sometimes the browser and the operating system are made by the same company. So like, for example, I'm using Safari on a Mac. And so the difference between whether it's Safari or the Mac is kind of blurred. Yeah. But basically the browser will farm it out to the operating system. If I go install Chrome, now Chrome has the choice. They could implement their own TLS support, or they could just farm it out to the operating system itself. I believe Chrome on a Mac farms it out to the operating system. Then if I download Firefox says, no, we're doing our own TLS. And so it has its own root store. It has everything like custom. And so then you're going to be using your browser's TLS libraries. Yeah. So it's up to the browser. The browser has the first chance to intervene, and they can decide to do it themselves or pass it on to the operating system.
Tor is like sort of a version of Firefox.
So Tor is a Firefox version. Yeah. Okay, so TLS version, what do I support? So here's the versions. So there's 2.0, 3.0, and at this point it was called SSL. So that's the older name of the protocol. At this point, Netscape was running it. 1.0 was internal, so they never released it. And then 2.0 was the first public release. Then it was taken over by the IETF. So they organized like a lot of internet protocols and standardizations. They changed the name to TLS. And the first version of TLS is 1.0. So it went from SSL 3.0 to TLS 1.0. And then the numbering now is by like 0.1, 0.2 kind of thing. So there's TLS 1.1, TLS 1.2, TLS 1.3, TLS 1.4. TLS 0.3 is where we are today. So it's the most modern version. And TLS 1.4 is being standardized. So they're arguing about what it should look like. Okay, so what you'll say is all the TLS versions you support. So you'll say, I know TLS 1.3, but maybe you're an old server that hasn't been updated since 1990. If that's the case, I can talk TLS 1.1, 1.0, even SSL 3.0 if you need me to. Okay, so for backwards compatibility, servers and browsers maintain support for lots of different versions. Okay. Now, some of these are insecure. So once you go back to 2.0, 3.0, 1.0 even, there's major problems with them. And so sometimes browsers don't want to support them, and servers similarly might not support it. Okay? And so I'll show you some concrete examples. There's a tool for seeing like what different servers support and things like that. But okay, so we'll send the TLS version. Then what I'm going to do is I'm going to send the encryption algorithms, the cryptography algorithms that I prefer to use. Okay, so I would like to do key exchange because it has forward secrecy as opposed to key transport. I like GCM. I don't want to mess around with the MAC, so that's my preferred. And again, I'll send a whole list. Okay, so these are called cipher suites. And this will come as a list. And TLS will also come as a list. And then I'm going to send a random number called a nonce. This is going to serve a security goal for us. We'll talk about what that is later. I'll get through the handshake first. Okay. So TLS is just going to look like one of these numbers. What about these cipher suites? What do they actually look like? So I can show you an example. So there's a website called SSL Tests. There's a bunch of websites that do this kind of thing, but this one's a good one. Although maybe a little slow. All right, so I'm putting in concordia.ca. It will run some tests on Concordia, and it will see what versions of TLS does it support, what cipher suites does it support, and a bunch of other tests, see if it's vulnerable to common attacks and things like that. I did run it earlier today. Sometimes it takes 5 minutes to run all the tests that it does, but if someone's recently run it, then it won't rerun it again. It will just cache the result. And worst case, if this doesn't work, I screenshotted it so I can show it to you. But I'll try and show it to you live. Okay, so it seems to not be working.
Sometimes it doesn't work because of the
Yeah, okay. I was on the landline, but and this, by the way, this measures like Qualsys go to Concordia themselves. It's not a connection between me and Concordia yet that it's measuring. But okay, I'll show you the PDF. I have it, luckily. All right, so if this had run, we would get a report like this. Okay, so first off, it gives a grade, so Concordia gets an A. So there's no problems really with much. There's a few things that could be mildly improved. It notes that the server does support 1.3, so that's the newest version of TLS. There's a bunch of information about the certificate that was involved. We won't concern ourselves with the certificate. And here's the protocols it supports. So it supports TLS 1.3 and 1.2. It does not support 1.1, 1.0, SSL3, or SSL2. So if you try to connect with an old browser that only supports one of these, then the website will not load for you. You'll get an error or something like that. Okay. Then it has a bunch of things that look like a bunch of gobbledygook, but this is those crypto algorithms that I was talking about. Okay, so in TLS 1.3, this is all the different combinations of encryption it supports, and in 1.2, this is all the combinations that it supports. And these combinations are in preferred order. So the server can either let the client choose what they want, or the client just says, this is everything I support, and the server says, okay, I have a list, and it's in order, and we're going to do the one that I prefer the most, that's closest to the top of the list, that also supports you. In TLS 1.3, there is only Diffie-Hellman key exchange. There's no key transport, okay? So they don't bother putting that in. The only thing that you get to choose is, are you using a block cipher or a stream cipher? So here I'm using AES, or I'm using SHA-20. What's the mode of operation? So here I'm using GCM. And then what am I doing for a MAC? So here I'm using Poly 1305, and then SHA-256 is the hash that works with it. And here I'm using what's called an HMAC, and the hash algorithm I'm using is SHA-3 and SHA-256. Sorry, this is SHA-2-384, and this is SHA-2-256. But okay, so you should be comfortable with what all of these things mean. FS here means that it's forward secret. Okay, so because we're doing Diffie-Hellman only in TLS 1.3, they're always all going to be forward secret. And then this doesn't tell you how long the keys are used in the signature algorithm. Okay, so they give you a bit more information. So the Diffie-Hellman is elliptic curve Diffie-Hellman. 25519 is a curve that it goes over. This curve was developed by the same person that developed Dan Bernstein, who came up with SHA-20 and Poly 1305. And in Diffie-Hellman, you have to sign. So what algorithm are you using to sign? Well, they're using RSA. And how big is the RSA key? It's 3072 bits. Okay. Then if we go down to TLS 1.2, it gets a little more interesting. There's like weirder combinations. So these are very similar. This is actually exactly the same cipher suite as the top one here. Okay, so we're saying ECDHE and RSA here because it's an option not to use that, and then this stuff is the same as this stuff here. But let's pick one that's like a little further down the line just to see something different. So here you see TLS RSA. So this is not Diffie-Hellman key exchange. This is key transport. So I'm using RSA to encrypt a key. The client just picks a key, uses RSA, and sends it. ARIA is some weird block cipher that you've probably never heard of. There's one called Camellia, and there's one called Seed. So there's a bunch of weird block ciphers. And then this is the key length. They're using in GCM mode. And then this is the hash function that's used in the SHA. These block ciphers are considered weak. And so this website rates them as being weak. Also, there's no FS beside them. Why is there no FS? Because it's doing key transport as opposed to key exchange. Okay, so you
FS is
yeah.
only in key exchange.
Exactly. So FS and key exchange have a 1-to-1 correlation. Yeah.
So if it's weak, like I'm trying to understand, like when you do updates on your operating system or your browser, like it's automatically gonna put you at the latest versions of stuff, right?
So
You
again,
don't even have to worry about all those other.
yeah. So this is in preferred order. Okay. So actually, I think they have it here. So here they show a bunch of different operating systems, and they show what would happen if you connect. Like, what would you end up negotiating based on what these support and what the server prefers. And you can see it's like green all the way down, basically.
Yeah.
And so you basically always end up with the top hit, or maybe you end up, if it's like a really old version of Android, you might end up with something different. But you basically get a good cipher suite kind of all the way down.
So if somehow somebody's using like an old system, then it'd be easier to, like, as somebody in the middle to decipher what's going on, right?
Correct. Yeah. So let's say that I have an old system and I only support this algorithm. Then I will end up being able to visit Concordia, and Concordia will talk to me with this algorithm, and then someone in the middle has a chance of doing something bad. Yeah. Now, these algorithms are all like, okay, there's worse algorithms that were supported in 1996 in TLS. There's even ones where there's no encryption. So encryption is just empty. And then there's ones that have really small keys, 56 bits. So DES is an algorithm that only has a 56-bit key. That's something that you could brute force. There's also structural problems with DES. It's something that, like, you don't even need a supercomputer like a MacBook. Might take a while, but it could probably brute force that type of key. Yeah. So these ones are, Concordia's like, that's why they get an A, is like even with the worst possible, it's still okay. But there are ones that are really, really bad. Yeah. I would show it to you if the website was more responsive. So here they have a list of the worst ones. So these are people who got like really bad ratings. I can try and click on one.
Bank.
Well, it has bank in the name, but you know, you can't always trust. Yeah, so this one supports RC4. So RC4 has some biases in how it works, and so it's just considered insecure. It goes all the way back to SSL3. SSL3 isn't generally, there's some problems with it itself. And so this one, for example, TLS RSA with DES, CBC, SHA. DES has a 56-bit key. You can see it over on the right. It says 56. 56 is like within the realm of, like, the amount of work it would take to guess every 56-bit key is less than, say, what Bitcoin does every 10 minutes. It solves like a problem that's way, way, way harder than that. So 56 bits is really not suitable. NIST says that you should be at least, the cutoff is kind of weird. They say 112, even though most ciphers round up to a perfect power of 2. So 128 is sort of the bottom for what would be considered secure. These ones, even though they're 128, they're insecure because of other reasons, because of RSA. So you can see if I come with a really old browser like IE version 6 on Windows XP, then I'll end up using this cipher suite.
What if we try to provide security patches for XP? It still would not be able to hold up.
No, so if you update just the SSL library so it has the support for the latest algorithms, then that's fine. Yeah, then it will end up supporting it. So that's the only kind of patch that you would have to maintain, is just keeping it up. Yeah. Okay, I'll copy and paste a few of these into the notes just as a reminder that you should understand. You should be able to look at this and tell me like what what something like this means.
On an exam, you have to do that.
Yeah, on an exam, you will have to know it. You have a cheat sheet, so you can. You don't have to remember what acronyms mean, but you should be able to parse what this out. Okay, I hope I have enough room to do the whole handshake, but I'll just kind of leave it down here. So I'll just dissect one of these. So this is Diffie-Hellman. RSA here corresponds to the signature.
And it's always in the same type of order.
Yeah, usually, yeah. This is the block cipher. By the way, I didn't show you what CBC is, but we'll see it before the end of today. And then this corresponds to the MAC. This means it has forward secrecy.
Key exchange.
Yeah, so key exchange, Diffie-Hellman and forward secrecy, again, will be, if you have one, you have the other. Yeah. And we don't have it, there's nothing with forward secrecy that's not Diffie-Hellman in TLS. Yeah. Here it's really small, but we have the bits 2048. This corresponds to RSA. So RSA is working with 2048 bit keys. This is below what NIST recommends. So right now, NIST recommends greater than 4096. That's NIST's recommendation. And that's why this whole line is yellow, because it's not considered, it doesn't meet NIST standards for that reason. AES 256 is fine, 256 is fine, but NIST recommends that, yeah. So NIST's recommendation here is greater than 128. So the block cipher should be at least 128. This is 256, it's even better. And then the public key encryption, there's faster ways than brute force. You can use some number theory attacks. And so that's why the keys need to be a lot bigger than here. But those are details that we won't worry about there and then there. Yeah.
Could you also explain on the first line the ECDH part, like at the end?
Here?
Yeah, that part.
Yeah, sure.
And why that one is weak compared to the other? I don't see.
Okay, just let me go through these one at a time. Okay, so ECDH is elliptic curve Diffie-Hellman. Elliptic curves are a way of doing anything that's based on the discrete logarithm problem. You can do over what are called elliptic curves. Elliptic curves are thought to have the same security level, but they're a lot smaller. They're more complicated to understand, but the resulting sizes of everything is a lot smaller. So things that rely on discrete log are Diffie-Hellman and the DSA signature. So you'll see either Diffie-Hellman or DSA have EC variants of them. RSA is based on a different problem, factoring the product of two primes, and so elliptic curves don't do anything for it. And then you have to pick a specific curve. And so there are a bunch of curves, and they all have different names. So NIST has standardized a bunch of curves, and other people like Dan Bernstein or whatever have picked them. And so this curve that it runs over is called SecP 256K1. I think, if I can't read it, but, oh no, it's R1. So that's like the NIST name for a curve, for a specific curve. So Bitcoin, for example, uses SecP 256K1 and then, yeah, but there's a bunch of different ones. And then there was, some people were using, I saw it was, I guess, in the TLS 1.3, but they were using 25519, so that's a different elliptic curve. It's just a different curve. Yeah. So that detail you don't have to worry about so much because, yeah, I won't test on the elliptic curve stuff. But yeah.
So who determines like the grade, sort of like the quality of the security? Is it like the developers or the server?
Okay. So there's two like ways that people are putting their opinion into this. The first is this website itself, like giving the A and saying this is green and this is yellow. That's not objective. That's qualsys. So they have people that think about SSL every day, and then they come up with these gradings. So that's their opinion about it. All these are objective facts, but like whether things are weak or stuff, like that's stuff that they decide. Like, is this a yellow thing or is it a red thing? Yeah. And then the order of these, Concordia decided. So Concordia, some admin or IP person or the software that they use, it decided that this is the order that we like to prefer things in. And generally, like, this is the most secure, and then this would be the least secure thing that we'd still be willing to do.
Do you have to pay for that?
So this you don't have to pay for. It would just come with the software itself. So like if you use Apache or whatever, OpenSSL, it would have some list. Somebody thought it up in the open source community and put it in. And then this website is free too, so you can go play with it yourself. Yeah. Okay, other questions? Okay.
Why one is secure over the other is just exactly what you just said, that elliptical curve Diffie helmet is more secure than that part of it?
Yeah, so things are weak either because they're using key sizes that are too small.
Okay.
So they're less than what it should be, or they're using RC4 because it is just a weak cipher. But the website itself will have some explanation of,
Okay.
there'll be some explanation somewhere of like what they consider weak and what they don't. Yeah. But those are generally, in fact, it might say here where, but. Okay. All right, so we're almost on the hello. So hi, I want to talk TLS. My highest version of TLS is 1.3. I support, so this is a list. So here's 100 cipher suites. I support them all. You pick the one that you want. Here's a nonce, a random number that we'll use. And then the other thing I throw in, there's a bunch of other stuff, but the other one that's generally important is I throw in something called an SNI, which is going to sound really stupid, but I'll explain why you do it. I'm going to say I'm connecting to concordia.ca. Okay? Why am I'm going to concordia.ca, I'm saying hi, and I'm telling it that I'm connecting to concordia.ca. Why would I do that? Doesn't it already know? So sometimes what web servers will do is they'll host more than one website from the same IP address. So just because someone shows up at that IP address, you actually don't know which website they're after. So then this SNI is a way of distinguishing different if you host multiple domains within the same website. So the client will just tell it which one it wants so that it knows. Yeah.
Is that like having different companies in one building? Like what you just explained, is it like having like, let's say, Microsoft, Google, Apple, in just one building?
So the IP address is given to you by your ISP. Yeah. And so generally, even within the same building, everyone who has an internet connection from the ISP will have their own IP address. So generally, companies wouldn't share it. The main thing would be like for example, let's say Concordia, they have Moodle.concordia, ENCS.concordia. They might all go to the same DNS. They're all they all belong to Concordia, but they are technically different domains. Yeah, so that's like the more likely scenario. The other time you see mixing is if there's a service like Cloudflare or what these CDNs that sit out, they have a bunch of clients, and so they're going to put up an IP address that will handle traffic. It's in Montreal, so everyone that goes to one of their clients is going to hit this one Montreal IP address, and then they'll have a list of all the clients that they support. Yeah. So SNIs become more important in the CDN context, but yeah. Okay.
What is SMS stands for?
Where? SNI, I forget. I know it's something identifier. But server name indication. Thank you. Okay. Then we're going to say hi back. Okay, so we'll have server hello. It's going to say, I see all the TLS versions that you support. Let's talk 1.3. So it will choose from the list. It might just drop the connection to if it sees something it doesn't like, but assuming that it sees something here that it's willing to talk, it will choose it. And then it will go through the list of cipher suites. It will go through its own list, and it will try and pick the one that's common and at the highest level of preference. So it will say, this is the cipher suite that we're going to use. And it's also going to choose a random number called a nonce, the purpose of which we'll talk about later when we talk about something called a replay attack. All right, so this usually comes in one sort of packet or record, and then it's going to send a bunch of stuff to the client, but it sort of does it in different kinds of messages, but they're all going at sort of at the same time. Now it has to send its certificate. Okay, and it will send actually a chain of certificates. So we'll send everything that chains back to something that's in Alice's root store. So Alice will get the certificate, say for Concordia, and then it might be signed by another CA, and then the CA certificate might be signed by a root that's in Alice's operating system. And so then it's happy. And from this, it's going to get the public key. Okay, so it has Concordia's public key out of the certificate. It's going to need the public key either because in key transport it's going to encrypt the key, or if they're doing Diffie-Hellman, it's going to get signed by the server, and it's going to use this key to verify the signature. Okay. What does it look like? Oops. So we have Concordia, global sign is the CA, and then global sign is also a root CA that's on my computer that signed Concordia.
That's the one that's on the Amazon.
Sorry, Amazon was signed by global sign, you mean?
No,
Okay, yeah.
So cipher suites, one of the things we saw on the SSL website.
Yeah, so cipher suite is this. I'll label it. So it's going to choose one of these things.
And here, 2048, for example, you said it's RSA, right?
Yeah.
Why it's written Diffie-Hellman?
It's RSA signatures on Diffie-Hellman.
Okay.
So in
there's
Diffie-Hellman,
signature.
in Diffie-Hellman, you have to sign something, and you'll use RSA to sign it, and the RSA signature will have a 2448-bit key. Yeah. We'll draw this out in a sec. Okay.
So, but I remember the certificate authority. Those keys are hard coded in the operating system. I looked at the folder
Mm-hmm.
on the brochure.
Yeah.
What's stopping somebody from forging something there?
So if your root store gets corrupted with bad certificates, you don't have security personally. So then now your computer will accept. It could accept certificates. So if an adversary can put their own certificate into
That's
your
what I
root
mean.
store.
Somebody would compromise that folder and put their own thing.
Yeah, so if that
That's
happens
possible?
to you, then you don't have any security. You can't form secure tunnels knowing that it's a tunnel that goes all the way to
It's like
Concordia.
It's an attack that's possible.
Yeah, exactly, yeah. And it's also a feature, sort of. I mean, so some people do it deliberately. So you mentioned Wireshark. It might do that so it can intercept. If you install antivirus software, it might want to look at HTTPS stuff to make sure malware is not coming down.
Yeah.
So it will do that. If you install parental control software, say for your kids, it could do that as well. If I work at Concordia and Concordia wants to monitor my traffic, they give me my laptop. So before they give it to me, they install one of those certificates on my laptop. Yeah. So those are called interception proxies. Yeah. Okay. Let me wrap this up and then we'll take a quick break. Okay. The only other thing it might do is it depends on the cipher suite, but assuming that we're going to do Diffie-Hellman, then it will also send its value. I'll write as, usually we go G to the A and G to the B, but A and B is sort of arbitrary. And it's going to sign that as well. Okay, so now the client has the first half of the exchange. The client has the key here out of the certificate. And so it will take the key, it will take G to the B, and it will take the sig on it. It will run all of that through the verify function of the signature. And it should hopefully get true back as a result. And the last thing the server says is, I'm done. I've sent you enough stuff. You don't need anything else from me. Sorry?
Verify key?
Yeah, verify true. True.
True? Okay.
So it like when you showed the Concordia before, when it does this for the whole stack in one shot of all of those like requests or what for files or folders or CSS and everything we mentioned. It does that once for everything, or does that each time?
So it does it once for each outbound connection.
So every time you write a new URL?
Not exactly. It will do it once to the domain concordia.ca, but then everything else from concordia.ca, it won't redo it. It will send it over the same tunnel. So a tunnel is a session. But then now I'm going to this Cassie Cloud, so I have to do a handshake with Cassie Cloud.
Every time it goes to a new server?
Yeah, so every time there's a new domain,
Oh, okay.
it will do one of those. So if, let's say there's 10 domains across this, I'm going to do 10 handshakes just to compose this website. Yeah, but once I have that session in place, until I navigate away or close my browser, or there's a couple ways where the session dies, then it will live.
And a cookie is just something is that related to this?
So a cookie is not a TLS thing. That's something that is it's related to passwords. There's different purposes for cookies, but yeah, in 6150 I cover cookies as well. You'll learn about that. Okay, other questions? Okay, let's take a 10-minute break and then we'll come back at quarter after. Okay, so just to recap, we say hi, we tell the version, we say what cipher suites we support. There's this nonce, and we say we're connecting to concordia.ca just in case you support more than one. Server says hi back, says, okay, I looked through your list. This is the TLS I want to talk. I looked through your list of cipher suites. This is the cipher suite I want to use. Here's another nonce. Here's my certificate. You'll see that if there's a long chain, I'll send you all the other certificates as well. So you can quickly see that you get back to a root certificate. If you open my certificate up, you'll see my key. Okay. If we're doing Diffie-Hellman, I'm going to send you my Diffie-Hellman exponent, and I'm going to sign it. And you're going to know it's from me because I signed it. And then I'm done. That's it for me. I've done everything that I need to do. And then what the client will do is they'll do one of two things. If it's Diffie-Hellman, they'll send G to the A, okay, so that it will complete the Diffie-Hellman. If it's key transport, now that they have the public key out of the certificate, then what they'll do is they'll encrypt with the public key of the server some master secret. They'll just pick the master secret itself. and they'll encrypt it, and then they'll send it to the server. Then what they'll do is they'll send a message called change cipher suite, or sorry, spec. It's kind of a weird name, but this just says we're now going to use encryption. Okay, so I have everything I need. I sent you everything you need. Now we can both come up with a key, and now let's switch over to encrypted communication. The next packet you receive from me will be encrypted. Okay, so now we're done. We're done negotiating. Okay, and so and so then the server will send back this basically a confirmation of the that it's ready to start encrypting things. Okay, and now that's it for the handshake part. Okay, so there's one last thing that's, well, it's sort of part of the handshake. Let me just make some space. Okay, so from this point on, we have the tunnel. Okay, we now have a tunnel. Now behind the scenes, what they did is they pulled out the master secret, or they computed G to the AB, and they generated all those MAC keys and encryption keys and things like that. So there's the going from the master secret to the keys. I wasn't going to write it out, but I'll write it out because I'm sort of writing everything out anyways. Let me just write it in a way that's more intelligible. So they'll do a KDF, and they're either going to run an extractor on G to the AB, or they're just going to take the master key that was sent here. I'll call it secret instead of a key. What they're going to do is they're going to append to this the two nonces. So there's the nonce from the client, and there's the nonce from the server. So they're going to kind of mix that in, and then they're going to output all their keys that they need. So the two encryption keys, the two MAC keys. Okay, and the client will do the same thing. So the difference between here is just this corresponds to Diffie-Hellman, and then this corresponds to if they're doing key transport. I'll just write nonces. Actually, I'll write not C and not S, because nonce underscore S and nonces look the same. So they have all the same values on this side, and then they can derive their keys. Okay, so now we have a secure tunnel. Both of them have keys. Okay, so they can start encrypting and macking information for each other. But just to finish it off, what they'll do is they'll send a message inside the tunnel. Okay, it's called finished. And what the finished message includes or is, I'll write it as it is exactly, it doesn't really matter, is what they're going to do is they're going to run a MAC using the keys that they derived over everything they talked about in the handshake. Okay, so what cipher suite was chosen, what TLS version, and things like that. Server's going to do the same thing. And the reason for this, we'll see in a second. Okay. Then the next message will be like, say, a request for index.html or whatever. Okay, and so at this point, it becomes HTTP. Okay, so you start talking about giving me this resource and here's that resource and things like that. So request response kind of thing. So rec and res means request and response. It would send the file itself. I'll just put those, I'll plant those two words in your mouth, or sorry, in your minds, because it will, they'll be the kinds of things that we see later. Okay.
That's like a API?
It's just,
REST API?
it's not RESTful, it's just normal HTML, or HTTP. It's just how you ask for things, yeah. Okay, and then the rest is just stuff that goes back and forth now inside the tunnel itself.
Are you going to explain how REST API fits into this?
No, probably not. It's something that's in the, it's more of like a web, how you want to set your website up.
Okay.
It has nothing to do with the protocols themselves. In 6150, I do talk about it though. Yeah.
So all the steps before the tunnel is to secure the tunnel, right?
Correct, yeah.
So is there any way to intervene in the middle to intercept that I can be the man in the middle so that I can,
Yep.
see what is happening?
Yep, okay, so,
If it's
yeah, no.
If that's the case, so what is the possible way to secure that attack, and how can what are the measurements I can take in order to stop that attack?
Okay, so question, if there's someone in the middle, can they attack the protocol? Okay, there can be someone in the middle. So I want you to always assume that there can be someone in the middle. Do they see everything that happens here? They do. Okay, so they see everything that goes back and forth. So all of this is public, and it's something that the man in the middle sees. Okay, so I'll just sort of draw it here, kind of like this. And so our adversary has access to all of this. They can read it. They can write as well. So they can change stuff too. Okay, so it's read access and write access. Okay. Now you mentioned an attack. Do you have a specific thing in mind?
No, the thing is, if you write it, you can detect it because you have the exponential part, if I'm not wrong, right?
Okay, maybe, but let's think about that. So the attack could be I want to write into it. Okay. Yeah.
Like, when I give that kind of attack,
Yeah.
like I know where you are going.
Correct.
So can't I do like a botnet on the server, like to bring down the server?
Yes. So denial of service is not something this will protect you from. Yeah. So if you want to stop me from accessing a particular website, this protocol is not going to help anyone. Yeah. So you can always stop me from accessing. If you have the capability of stopping me from accessing it, doing things over a secure tunnel or not won't solve that. Yeah. So it's not one of the properties of a tunnel itself. So we have these properties, but we don't have a denial of service kind of thing. Yeah.
So if somebody actually is verifying in the middle, they're just going to see like gibberish going by, right? In terms of
This is not gibberish yet. This will be once the tunnel's set up.
Okay.
But everything in the red is well structured.
Oh, okay.
It's all plain text. Yeah. Yeah.
If I think we have attack on the DPML key exchange,
Uh-huh.
and if we got the keys, then the tunnel is not secure.
So if you get the master secret, the tunnel is not secure. That's correct. But how can we get the master secret out?
You explained it last time.
Yeah, so there is an attack like a man in the middle, but the signature here is going to break that particular attack.
With the with the apostrophe. when you explained it last class?
Okay, I did explain it.
B prime, A prime.
Oh yeah, exactly, yeah. So there is an attack if we don't have this signature here. There is an attack on it, but this signature will fix that attack. Okay. So let's go back to the other attack. Well, let's go to your attack. So your attack is I want to go in and change things. What are some things that I might change? Okay, so let's say client says I want to speak TLS 1.3. I change it to 2.0. They say I want to do AES GCM, with Diffie Hellman key exchange. I say I want to do RSA key transport with DES. Okay. Then what ends up happening is we set up a tunnel and now we have a 56-bit key. Yeah. Now I can break that 56-bit key. Okay. So we call that a downgrade attack because I'm downgrading the quality of the service. And you can downgrade anything you want about the connection, but the TLS version and the Cipher Suite are the two obvious things. But anything, it applies to anything in there that you might want to change. Okay, so we assume that there's an adversary is in a man-in-the-middle position. So they downgrade the client message to weaker version or Cipher Suite or both. Okay. And then they basically just pass everything back and forth after they do that. So they pass the messages. Okay, so the client will say, I support all these Cipher Suites. The adversary, they might pick one that is actually supported, okay? Like say they happen to support DES, but they get rid of everything else. Then the server will say, okay, we're doing DES. The client won't be like, that's weird, because the client said, I do support that DES. It's kind of weird that like you went to the very bottom of my list and picked one, but I do support it. And maybe there's a problem on the server side. Maybe the server is really old, right? And so it doesn't know that it's weird, okay? So everything is okay. So we downgrade to a weaker version or Cipher Suite. We don't do something that's not in the list, so it is in the client's list. Okay, so it's in client's list. So I'll just give an example. So here's the user. This is in the client hello. Okay, so they say, I support SSL 3.0 all the way to TLS 1.3. So I'll support anything in here. And I support a whole bunch of Cipher Suites. So I'll just write strong, weak. Okay. Then it will hit the adversary in the middle. And what the adversary will do is they'll delete all the strong Cipher Suites, and they'll just leave SSL 3.0. And they'll go through this list and they'll just put in the weak one. Okay. Then the server will receive, I speak SSL 3.0. I only support this weak Cipher Suite. Now the server might not support it, in which case the attack doesn't work. But assuming the server supports it, then it will choose it. And it will say, okay, let's do SSL 3.0. And we'll do this weak Cipher Suite. All right, so now both sides. The client is not unhappy, like I say. First off, it's a machine. It's just a browser code. So it's not like the human user is looking at it. And it did end up with something that it supports. And so it might think it's odd that it went all the way to the weakest one, but other than that, it's fine. It's in protocol. It's acceptable in the protocol to do this. Okay? All right, so that's the idea of the downgrade attack. Does that make sense?
Yes.
Okay, how do we prevent it? Or you can ask a question about it first.
So I was thinking, has there been any like successful attack on like the root CA? And if so, what does that really translate to? Does that mean everything is compromised? Like,
Okay.
there's no point?
So going back to this whole certificate chain, there are 100 attacks on this. Like these three things from here to here, there's 100 attacks. For the purposes of this course, I'm going to assume that that works, that there aren't attacks there. If you want to take 6150 with me, I'll spend 3 lectures on all the attacks there, kind of thing. So it's, or I'll put the video on Moodle and you can watch it.
So one,
But
one
yeah.
of them would be to actually go into the folder where the certificates are and add something there. Right?
Yeah, so if you compromise the root store,
Yeah.
then that's one of them. Yeah. And then there's a bunch of other ones. It's a whole like topic in and of itself. Yeah. I'll show you, actually what I'll do is I'll show you the attack tree that we developed in the other course. I'll paste it into the notes and just to show you the breadth of different attacks that are possible. But. Okay.
But you would have to have, like,
Back to the downgrade. How do we solve this?
administration. Yeah, exactly.
Yeah.
Like, just the server would like ask the client, did you send like using TLS 1.3 or was it someone else that changed the version? So it kind of verifying.
Okay, so the way that we solve it is basically first we get a key. So we're going to get a shared key. Okay, I'll get to that in a second. So, sorry?
Pre-shared key?
No, just because I'm forming the tunnel, even though I'm going to end up with a weak tunnel, I still will have a tunnel. Okay, so this is what will happen. So the Alice and the server will talk. There'll be an attack. They're going to end up with a weak tunnel because of the downgrade itself. Okay? Now, there's one thing that saves us. Everything about the encryption that's used is negotiable. Okay? But the MAC itself, until TLS 1.3, was not negotiable. You can't negotiate the MAC. It just was fixed. Okay? And there was no weak MACs. The MACs were always strong. So the weak tunnel was always weak in terms of encryption, or I'll put in terms of confidentiality, but not integrity. And that's just because the integrity was sort of hard-coded. And this is sort of by accident. I don't know that people were necessarily designing it this way, but it's the way that it was. So you have hard-coded MACs, and they're basically all secure, even today. Even the oldest version of SSL 3.0, the MAC in it is fine. It's the one thing that's like survived. Okay, so we have a weak tunnel, but we have the ability to do a secure MAC, even though everything else might be compromised. Okay, so then what do? What we do is we basically, the client will say to the server, this is what I heard, this is what I told you. I told you I support all of these cipher suites and all of these TLS version numbers. Okay, so I told you I support everything from SSL 3.0 to TLS 1.3. And I support all of these cipher suites, strong, strong, weak. And everything else. There's more to the connection than that, but basically all the things that matter. Okay? And what it's going to do is it's going to MAC this information using the key that it set up.
So then you can't change it.
Yeah, so now what happens? The server looks at it and says, oh, you said SSL 3.0 to TLS 1.3. That's weird. I heard you say just SSL 3.0. That's why I chose SSL 3.0, because I didn't know that you supported TLS 1.3. Oh, it's weird. You're telling me now that you support these strong cipher suites. That's not what I saw. I saw that you just supported the weak one. Okay? And so the adversary will get caught. Okay? Similarly, the adversary might try to downgrade here. So they might let the client hello go through, but then when the TLS and cipher suite come back from the server, then they might downgrade it at that point. So the server is going to do the same thing back. The server will say to the client, this is what I told you. I told you that we're doing SSL 3.0 and we're doing weak or whatever. And the client might say, oh, that's weird. Like that's not what I heard from it.
So
Yeah.
it won't accept that.
So it won't accept it. One of the two won't accept it, but they won't realize it until the end, until after
Is
the
this
tunnel's
done
set up.
every time?
Yeah, every time. Yeah.
That math part of it?
Yeah, and you'll notice, just let me say, I already wrote it into the protocol. So I said there's this finished message, and it's a MAC on the handshake. What I mean by the handshake is everything that happened before. Okay? So this catches the downgrade attack right here. So this prevents downgrade. Okay, questions? Okay. All right, so it's very important that you do that step at the end. And it was important that the MAC was never compromised. If you could downgrade the MAC, then big trouble for TLS. It would have been in big trouble. But so it was happy coincidence that you couldn't do that. Okay, now there's one other basic attack that I'll talk about, and then we'll look at some complicated attacks. All right, so a replay attack is another, first off, downgrade attacks, it's working here on HTTPS, but almost any protocol that you do that has more than one version number or has any options to it, you can do a downgrade attack. So downgrades are very common. You see them all over network security. Not even network security, it could be OS security or things like that. Another really classic attack is a replay attack. Okay, so the idea of a replay attack is, let's say that Alice goes to Amazon. And she buys something. So they have this whole conversation that's her like logging in and then putting something in her cart, pressing buy, whatever. Okay, so it's a big long conversation, but in the end she ends up purchasing something. The adversary's in the middle and just makes a copy of that conversation. Okay, then the adversary comes back. So the adversary will make a copy. Now, the adversary is happy because Alice is buying something that maybe the adversary is selling. And the adversary would like Alice to buy 100 or 1,000 of them instead of just one. Okay? So what the adversary will do is she'll just replay that message as if she's Alice. So whatever message Alice sent, she'll replay it. Starting from... she might do it from a different IP address. So maybe not going all the way back to here, but starting here. So she'll say client hello, TLS version, cipher suites, knots, all that stuff. It'll just be a direct copy of what Alice sent the first time. The server is going to respond with something. It might be the exact same thing, right? If she sent the same thing to the server is not going to change which cipher suites and things like that. So it'll probably send the same copy. And then they'll go back and forth. And if everything ends up being exactly the same or identical, they'll end up with the same keys. Then all of that traffic, Alice can't read the traffic. Okay, or sorry, the adversary can't read it. She can't decrypt the traffic. Somehow she knows that it ended up in a purchase, but she'll just basically replay everything. And then Alice will end up doing the same thing that she did before. Okay, so they'll replay handshake. end up with same keys or end with same master secret. We have to interrogate whether this is true or not. Then you'll have basically the same tunnel. I'll write it as same keys on either side. Then you can replay the messages. So she sends a copy of it, say times 1,000 to Amazon. Okay, let's say that Alice runs this protocol once, then she comes back tomorrow and runs it again. Is the conversation going to be exactly the same, or is there some difference between the two? Okay, what changes?
The timestamp?
Okay, so the nonce changes. The timestamp could change as well, but I could still replay it with the old timestamp, and then the server is just going to think my clock is out of date. But it's not going to be like I'm not going to sell something to someone with the wrong time. It'll just say it's weird, but that's okay. Yeah. So this nonce is going to change. That's one thing. What else could change? So which, and specifically?
If DH, we are using
Yeah, so G to the B will change. Yeah, so it'll change a different B, okay? What if I use key transport instead? Now it's not going to change, right? So the key transport, this client is picking the master secret. If I'm replaying Alice's, I'm just replaying whatever she picked, okay? So, okay, so DH stops this. Because G to the B will change. Key transport does not stop it. Okay, so then this is in general, like we solve this problem the same way in every protocol. Almost every protocol has a replay attack, and it's always solved the exact same thing with a nonce. Okay, so that's what that nonce is. And specifically, it's going to be the server's nonce, because the client, you're just going to replay the clients. So what's going to happen is the first time you connect, you'll have a transcript. Second time, I'm going to replay everything else. So I'm going to replay this exact message, including the nonce. But the server is going to send back a different nonce, okay? And now because I have a different nonce, I can get all of this stuff back, okay? And assuming I'm doing key transport, I'll replay all of this. But eventually I'm going to have to derive this key, and one of the inputs to the key is the server nonce, okay? So if the server changes the nonce on me, I'm supposed to change it here, okay? And if I change it here, I'm going to get a completely different key. So the server is going to end up using a different key than what it did in the first round. Okay, so this little tiny thing right here, I'll do it in red. This value right here is what stops the replay attack. I should have done this in red, but I'll just put it in box. Okay, so these two things were something that we added to the protocol to prevent downgrade. The nonce is something that we add to the protocol to prevent a replay attack. And the client also does a nonce. You could try to replay the server back to the client. That's another thing. Like say the client is trying to go to the server and you're in the middle, and you might, for some reason, a different scenario, you might want to replay back what the server told it the first time. So anyways, they both have nonces for that purpose. Yeah.
The server save notes?
Does it save it?
Do they save notes? Like, do they remember, like, at least?
Yeah, so they save it until they do this. So they do have to save it from this flow to this flow. They have to save it. Once they have these keys, then they delete it. Yeah. And for this, the client just has to remember it for, like, it receives it and then it uses it right away. So it doesn't actually have to remember it between. But yeah, memorizing things is something that we try to get rid of. We like protocols where you don't have to remember something that you did before. Because if you're Google, you have, I don't know, 1 million people connecting to you every second. You don't want to remember stuff, right? So we're always trying to make things stateless, which just means that you don't have to remember things. And we'll see that when we run this over UDP with Quick. There's going to be a bunch of changes that we make to make everything stateless. It's going to be like a recurring theme.
Question about so now the connection for the guy in the middle is like we know he can't understand, but the ISP on their end, because they're getting all the traffic is going through them. Like you mentioned the ASs and all that.
Yeah.
But like specifically the ISP, do they store information about everything in clear text in order because I know you hear about the government and all that going through.
Yeah. So generally ISPs might store, they have server logs. So they're logging a bunch of stuff that's happening. They'll keep the logs around for a while in case law enforcement wants to come back. Okay. They're not going to store like the whole handshake itself.
Like all the stuff?
Yeah, all the stuff. They'll generally just store that Alice went to this IP address at this time. Okay. And there might be a little bit more level to it. Or if they think there's something weird going on, then they might store more as a result.
And then if you're going through like Google or Facebook or these type of sites that are owned by like the corporation, they'll store information on their server.
Exactly, yeah. So they could store stuff too, usually not down to the actual negotiation, but they'll just keep track of every IP address that visited and what time and how long the session lasted, how much data went back and forth, maybe which websites they looked at and things like that. Okay. Yeah. Okay, but if law enforcement can get there before you go to the website, like say they're investigating you, then they can get a warrant and tell the ISP to log everything.
Oh, okay.
Yeah? Or if they're intelligence, yeah, if they're NSA or something, then they might actually be storing all of this because they're hoping to break it in the future. Yeah? So they're not like normal law enforcement, like just doing, or they're not a normal ISP. They're like a spy agency or whatever. And so there is speculation that they're doing exactly that.
Other governments.
Yeah, exactly. Oh, sorry, it's not just the NSA. The NSA is doing it to every other government, and every other government's doing it back. Yeah.
Yeah, because I see it sometimes they use in a court of law, like you see these crime reports and stuff like that, where they use it in court of law. It's how you search this on Google at this time. And
Yep.
stuff like that.
Exactly. Yeah. Yeah. Exactly. So Google will remember all your search history, and there's lots and lots of criminal cases where someone's like, how to dispose of a dead body or whatever, and they're searching that, and it doesn't prove anything, but it's highly circumstantial. It adds a lot of circumstantial evidence to it. Yeah, it's that too. Yeah. Yeah. Okay. So use Tor if you're going to do that.
Yeah.
Although that might not
But
be
even
enough.
Tor, yeah, that's a whole other discussion.
Okay, I'm going to show you two other attacks. Since this is a crypto protocol course, I'll show you two attacks that are not, these ones are sort of on the outside. Like, to understand these two attacks, you don't have to understand how AES works or how anything. They have to do with the handshake itself. These ones we're going to drill into the details of the crypto a bit. Okay? So I'm going to show you one called padding oracle attack, and then I'll show you another one called Beast. And then there's a million other attacks that are similar in flavor to these two attacks. But these are two good representatives. And they're related to each other because both of them assume you're using a block cipher. It doesn't matter. It doesn't matter if it's AES or DES or whatever. But the important thing is that you're using something called CBC mode encryption. So this is a mode of operation. All right, I'm going to grab a picture from Wikipedia or somewhere if I can find one. And then I'll write it out in equation form, but it probably... It's probably easier to visualize it before I write down the equation itself. Okay, so we have an encryption algorithm, and then we're going to have a decryption algorithm as well. And they're obviously they're meant to be compatible with each other. Okay, if you have not taken 6110, you might be wondering what all this is about. If you have taken it, why do we have a mode of operation? What problem is that solving for us? So there's two problems it's going to solve for us.
One is if the text size was bigger, but our encryption is 256. So
Okay.
we have to make it block by block.
Okay, great.
One is
All right, so any encryption algorithm, say AES,
256.
it takes...
192, 256, 128.
Exactly, yeah. So there'll be different like versions of it, but they will have some upper limit, and the biggest is it will take a message of 256 bits. That's called a block. That's why it's a block cipher. And it will output a ciphertext of the same size. Okay? If your messages are less than 256 bits, that's fine. You just use AES, you're done. Okay? But what if you want to encrypt something that's bigger than 256 bits? Okay, so you need to break what you want to encrypt up into blocks, and then you need some mechanism for invoking AES on each block. Okay? So the mode of operation, it doesn't necessarily have to be CBC, but it has to be something. So the mode of operation handles more data. Yeah, so that's a different mode as well, block by block. So yeah, I'd say there's three modes that are pretty common. So the one we talked about is ECB. ECB is literally just take your first block, encrypt it, then take your next block, encrypt it, then take your next block and encrypt it. And the problem with ECB mode, yeah, is the output, if the input's the same, the output's the same. So you get something that looks like this, like that's an encryption of this image. Okay. So what we want to do is we want to encrypt the first block, but then we want to like somehow feed that into the second block so that it messes the second block up. So that the second block, so it won't be the same. Yeah. So that's why you see this sort of feedback here. So I take the first block, ignore the IV for a second. I take the first block, I encrypt it, I get my ciphertext, but then before I encrypt my second block, I mix in the ciphertext from the previous block into the next block itself, okay? This operation right here is called an XOR. You can think of it as addition mod 2. You can look up what that means, but basically if it's a 0 and a 0, it goes to 0. If it's a 1 and a 1, it goes to 0. And if it's a 1 and 0 or 0 and 1, it goes to a 1. Yeah. Okay, so you do an XOR. And if you XOR, first off, the output here is going to be random. Once you pump something through a key, because the key's random, okay? So the key's random. I encrypt with a random key. I'm going to get a random looking thing out here. So I'm going to XOR something that's probably not random. Your plain text could be like something that's structured. But once I XOR it with something that's random, so something random goes in, we'll say this is not random, then the output I get here should be random. Okay, so mixing together randomness with non-randomness results in randomness. Okay, and so a stream cipher is the same. That's basically, all you do is actually you just take your key, use a PRG and make it as big as your message, and then XOR it with your message. And then to decrypt, you do the same thing, and you get it back. But anyways, block ciphers are a little more complicated. Okay. Now, here, what are we XORing? We're XORing the previous ciphertext value. But what do we do on the first block? The first block doesn't have a previous ciphertext value. Okay? Yeah, so what we do is we just choose a random value, and we use that on the first iteration. Yeah, like a salt. Yeah. So it's an IV, and this is public, so you send it with the encryption itself. So you say, this is the salt I used. Okay? Now, the IV has a second benefit. It means that if you encrypt the same message twice, like say I encrypt it today, and then 5 minutes later I encrypt it, I'm going to get a different ciphertext because I choose an IV. I'll choose a different IV the second time I encrypt it. So this is like randomly chosen.
Can we use STR instead of CBC here?
STR is what?
Counting.
CTR, yeah.
CTR.
So CTR is a different mode of operation that has the same properties. It also has an IV. It also has a way of chaining.
It works in parallel, I think.
Yeah. So it works a little different. I can show you what it looks like. We won't dwell on it because the attack that I want to show you is on CBC. We're going to use the properties of CBC. But I apologize. I guess it doesn't have an IV. But yeah, all you do is you have like sort of, well, it has a nonce. What you do is you put your IV through the encryption, and then you XOR the results with your plaintext, and then you go to the next one and you increment your nonce by 1, and then you increment it and then keep going. Okay. So this whole top half is actually a pseudo-random number generator keyed with the key. The output of all these blocks is random, and then by XORing it with the plaintext, you're making a stream cipher. So it's basically a way of making a stream cipher with a block cipher. The big advantage of this is, let's say I want to just decrypt the third block. For some reason, I don't care about decrypting the first and second.
Yeah.
I can compute what the counter should be set to, and then I can just decrypt the third one. If I go to CBC, because everything's chained together, I can't decrypt the third one until I've figured out what the second one is, until I figured out what the first one is, until I figure out what the IV is. So you have to...
They are in order.
Yeah, you have to decrypt it as a sequence. So the main reason people prefer counter is just you have random access to the ciphertext. But otherwise, the security of them are exactly the same.
So mainly they work the same.
They have the same properties. They both are CPA secure. Yeah.
Not CCA.
Neither of them are CCA because there's no MAC.
Yeah.
So what I can do, and this is actually going to be the problem. We'll see. Yeah. Okay. So IV is random. And it also means that encryption is non-deterministic, or I'll say encryption is randomized. So if I encrypt the same message 10 times, I'll get 10 different ciphertexts because each time I'll use a different IV. If I encrypt with the same IV, I will get the same result. Okay, so same IV will give you the same result, but I'm supposed to change the IV every time and choose it randomly, and so then I'm going to get different ones. Okay, so I'll note here that this is CPA secure, but you'll have to go back to like 2 lectures ago to remember what that means. Yeah.
What is the mode of operation then? What is the
Sorry, handles more data block by block. Okay, so mode of operation, it's just there to, if you have more than 256 bits, it's there to chain everything together, and it also gives you randomized encryption itself. Okay. All right, now we do use MACs in TLS. Okay, so this is what I'm going to assume, and this is something that was supported. Okay, so I'm going to assume. I'm going to have a bunch of assumptions. So the first thing I'm going to assume is what I do is I take my my message. I MAC it. All right, in capitals. I'm going to MAC it with the MAC key. I'll write that KM, so this is the MAC key. And then what I'm going to do is I'm also going to put some padding on the end. I'll talk about that, why it's there. But basically, I need to get it so that it fills up. I can't have like something that's less than 256 bits. So I'll fill up the message. Then I'll put in the, I'm putting it in the wrong spot. So at encryption time, say my message fills up the first block, it fills up the second block, it fills a few bytes of the third block. Then I'll append my MAC, so that will fill up some space. But then I might have some space left over. So I have to do something with that space. So what I'll do is I'll pad it. And I'll show you what the padding is. Okay. Then what I'll do is I'm going to call this P for plain text. Then what I'll do is I'll encrypt with my encryption key the plain text. Okay. All right. So what I'm doing here is I'm taking the message, I'm computing the MAC, padding it, forget about it for a second, and then I encrypt the whole thing. That's a way to mix together an encryption function and a MAC function. Now I have confidentiality from encryption, and I have integrity from the MAC.
And you said it could be done in a different order.
Yes, so thank you. So we call this order MAC, then encrypt. So I MAC first, and then I encrypt the MAC. Okay? I could do it in the opposite order. What I could do is I could take the message and pad it, then I could encrypt it, and then I could compute a MAC of the ciphertext rather than a MAC of the plain text. Okay? And it's going to turn out that that's going to be better. So you might think they're equivalent. They look kind of the same. But this attack will show you, first off, it's not the only reason this attack works. There's a bunch of things that go wrong. But if you were simply to switch it to encrypt then MAC, this attack would go away. And that's what TLS did. Okay, that was one of the changes they made once this attack was discovered. But anyway, so we'll go through the attack first and then we'll think about it. Okay, so this isn't the only way of doing it. It's just the way they happen to do it. Okay, assumption 2 is padding. I'm going to assume that it looks kind of like this. First off, let me just draw kind of like what the whole thing looks like. So this is my first block, and it's filled up with data. Then I have a second block, and it's filled up with data, but then I'm done. Okay? Now what I have to do is I have to put my MAC here. Okay? And it will take up some amount of space. All right? It may spill into other blocks, but anyways, we'll just, for simplicity, we'll draw it like this. Now I have a bunch of space at the very end. Okay? I have to put something there. So I'm going to pad it. What am I going to pad it with? Well, there's different schemes that you can use. Okay? The scheme that we used in TLS looks like this. I figure out how many bytes I need to pad. So let's say I have 5 leftover bytes. What I do is I just write the number 5 in each of them. So I'll have 5 5s. Okay? So the padding is, so for p bytes, I write 0x, just meaning in hex p times. I don't know that you'll be able to read this and understand what it means, but basically it'd be 5 5 5 5 5. If I wanted to pad 4 bytes, I would write 4 4 4 4 times. This is a hex number, yeah. So this is a byte. So what's the smallest value of a byte? What's the biggest value of a byte? Okay. Or FF if you want to do it in bytes, 00 to FF. Okay, so that's how we're padding. Okay with everyone? All right, now I'm going to make a third assumption. Oh, I'll make another assumption, which is, I already kind of made it before, but I'm going to assume that we're using AES CBC. I'll put C above. Okay, and then the fourth assumption is I'm going to make some assumptions about error handling. Okay, so let's say I receive a ciphertext, I go and decrypt it, and it's junky. Okay, what went wrong?
Lost bytes.
Yeah, I lost bytes or something like that. Okay, so what would I see when I go to decrypt it? So what I would do is I would first apply my key to it. So I don't have the decryption written out, but I would apply my key. I will get something out at the end of the day. If I apply the key to it, I will get something. Okay? And then I'll try and parse it like this. Okay? So I'm looking at something that should be formatted like that. What could go wrong? So if I check the MAC might not hold. Okay, so then I would throw an error. What about the padding? Is there such a thing as bad padding?
Yeah.
Okay, what's an example of bad padding?
If it's less than the total number of bytes you're expecting.
Okay, maybe, but there's something else that where you can just look at the padding and say that's bad, something went wrong. So what if I saw, instead of 005, I saw 004? 05, 05, 04, 05, 05. Is that valid padding?
No.
It's not 5 copies of 5, okay? And it's not 4 copies of 4. I don't know what it's supposed to be, but that's not valid padding, okay? So the padding could be bad, or the MAC could be bad. What would I check first? Okay, I can't check the MAC actually until I pull it out, right? So I don't know where the MAC ends, where it starts and ends. I know how big it is, but I don't know where it ends until I figure out the padding. Everyone see that? Okay, so I can't, it's a great answer, but I can't actually check the MAC until I get rid of the padding, because that's how I find the MAC. Okay, so what do I check first? The padding, okay, by necessity, okay? So I have to check padding. Before the MAC, before I can parse the MAC. Okay, so if I see the padding's bad, I'll just throw an error and I'll say padding's bad. Okay, so I'll say padding error. If the padding's okay, then I'll extract the MAC. And then I'm either going to throw a MAC error, or the MAC is fine, then I'll decrypt it and I'll believe whatever I saw. Okay? And there's no chance that if the message gets changed somehow, like say a bit or something, that the MAC won't catch it. That's the cryptographic guarantee of the MAC. Okay?
So if the MAC catches it, then in the TCP handshake, it's going to go back and tell them that it's not going to send an acknowledgement, basically, right?
So it will throw an error. It won't happen. It's not going to happen way up here.
Okay.
It's going to happen, say, well, it depends where the error is, but it would be somewhere in the tunnel itself. So it could be at this stage, but all of these requests and responses, because they're going through the tunnel, I'm assuming that it's happening over CBC mode with a MAC. So it's the data now. So it's the like give me index.html or here's index.html. That's the stage that we're talking about at this point.
So it's gonna be like a 404 error or something?
So the error will be handled by the TLS library.
Yeah.
So it will say there was an error decrypting. And then what TLS will do without you knowing it as a user is it will just go back to the server and say, there was an error, can you send that again? And then it will send it again, and it will keep sending it until you can decrypt it. So you won't get a 403, you won't get anything in the browser, unless if you like go digging, like in network tools, there might be like a log that will show that that packet was corrupt. Okay?
I don't remember. Yeah, I never checked.
All right, so this is the setup. We don't have time, obviously, to go through the attack itself, but we'll stop here. Next class, I'll remind you of the setup of the attack, and then we'll put through the attack. If you're very ambitious, you might look at this. You have enough to come up with the attack yourself. So you might look at this and try and figure out what the attack is going to be. Everything you need is here, but this is a bad combination for reasons that we'll talk about. Okay, we'll see you all next week.